Hey everyone, welcome back. Mr. Allen here. We're going to go into proving and verifying trig identities today. I guess you can see that from the title. So trig identity, from what we've seen, is essentially an equation for which all values in the domain are valid. Normally, again, when you're solving an equation, you're looking for that one or those possibly two or three answers that make the equation true. In the case of an identity, all values that are legitimate, all values from the domain will give a left side and a right side that are equal. So sort of the key here is to prove the identity, we always have to work independently with each side. So when you have an identity, or when you're trying to prove that an identity exists, so not one of the ones you're given, but something new, if you're trying to prove that this is equal to that, we always have to work with the left side individually and the right side individually. You'll see that in a second. The reason for that is pretty simple. If I'm stating that two things are equal and they're not, then I'm a liar, and mathematicians are not liars. They might be a lot of things, but they are not liars. And so we don't want to be liars because we want to be true mathematicians. The basic trig identities we have to work with, the Pythagorean identity, the quotient identities, and the reciprocal ones. These are the ones you've seen already. They're on the next page as well. And we can use those to prove more complex identities. And basically, just a quick comment that trig identities can be used as simplified solutions for problems that result where trig expressions exist in other fields as well. So to go about proving trig identities, this is essentially what I would suggest. Now, some of these things won't come into play. Certainly, all of these things don't come into play on every question, but they're things to consider. First one, separate into left side, right side. That is absolutely mandatory. We will always do that. Simplify the more complicated side first. That seems like the best place to start. Always express reciprocals in terms of the original three, and express tangent in terms of sine and cosine the majority of the time. That doesn't mean you have to do it right away. Sometimes you can sort of see that I can expand something or I can work with something a little bit first, but often that's where we'll end up. If you have some sort of a rational expression, find a common denominator and basically put the two pieces of the expression together as a single fraction. Factoring is something we've done a little bit already and we've done previously, certainly still something to consider. And if you get stuck on one side, switch to the other. Often you'll start on the more complicated side and get to a point where it's fairly simplified and you can see that it's now more simplified in appearance than the other side was. Jump to the other side and go with that. And then the Pythagorean identity works both ways. If we see sine squared plus cos squared, we will replace it with a 1. But occasionally you'll have to do the opposite as well. So using the Pythagorean identity, replace a 1 with sine squared cos squared. Kind of a last resort, but something still that we want to consider. And again, these are just the fundamental trig identities that we have available to us as we do these questions. So this is the type of question we'll be looking at today. Prove that this is equal to this. Okay, so again, very different from the identities you've seen, the fundamental ones that we just saw on the previous page. Those are things that have been established that we use as rules. This is one that we're trying to establish is also true. And so the question is basically, if we look at this, given what we just saw, what should we do first? Well, I would say looking at it, the left side here is considerably more complicated than the right side is. So I'm going to work with the left side. And so left side is equal to this, and this is kind of the way we'll set it up. You'll see what I'm doing over here in just a moment. And then basically, I want to use the trig identities that we've seen before to do some sort of a simplification to this. Now the question, of course, is what should I do first? And one possibility would be we have tan squared here. We know that tan is equal to sine over cos, and so substituting there makes perfect sense. Over here, exact same question. If I look at it, I see that I have two binomials being multiplied, and so multiplying through tan squared times cos squared and so on seems like it makes perfect sense as well. A couple of other possibilities. Down here, what did I do? Cos squared minus 1 is a sort of a rearranged version of the Pythagorean identity. If I factor out a negative 1 here, then I have negative times 1 minus cos squared, so sort of the reverse of this as far as the signs go. 1 minus cos squared is the same as sine squared. So I probably should have done that in 2 steps, but essentially cos squared minus 1 is the same as negative 1 times sine squared, or just negative sine squared. So that actually makes pretty good sense as well. And finally, over here in the blue, we know that 1 is the same as sine squared plus cos squared, and so maybe less logically, but still mathematically seemingly correct, I replaced the 1 by sine squared plus cos squared, the 1 over here by sine squared plus cos squared. So 4 different ways to go about starting this, and certainly I could have come up with some others as well. The question, of course, is which one is okay and which ones are not. Which one is right, if you will, and which ones are not. So we'll take a quick peek at them individually. Purple one here. So I did that first substitution, tan squared becomes sine squared over cos squared. And then sort of what do we do next? Well, I see again the 2 binomials, and I could multiply through this term times this term times this, and so on. So I've got my 4 steps of my expansion. The reason I kind of liked that, or it seemed like a reasonable thing to do, was my first expression here, the one that maybe is the ugliest of the terms that I have, sine squared divided by cos squared. When I multiply by cos squared, I've got a multiplication and a division, so cos squared will divide out with the cos squared there. And so now I have a sine squared plus a cos squared minus a 1, excuse the handwriting, sine squared x plus cos squared x, sort of just rearranged a little bit. And of course, sine squared x plus cos squared x is 1. I now have 1 minus this expression, minus a 1. And that gives me negative sine squared over cos squared. Now there's not much more I can do here. So often, sort of once I've simplified to a point where I'm pretty satisfied with what I have, what I'll normally do is kind of refer back to the original question and see what the right side looks like. It's negative tan squared. And so negative tan squared here. That wasn't very effective. And negative tan squared, we know, is the same as negative, and tan squared is sine squared x over cos squared x. And this is sort of how we finish up now, recognizing that, of course, the left side and the right side are now showing to be exactly equal. Initially, remember, I was trying to prove that they were equal. Now I can clearly see that if this is exactly the same as this, so this is equal to this, again, that's what this statement states, and that this is exactly equal to this, and this, and this, and this, and this, I then finish up by saying this is equal to what's on the left side. In other words, at some point in time, the left side was exactly the same expression as this one. And then this is going to be the big key right here. Once we've done that, we have to establish that we knew what we were talking about and that we're awesome, awesome mathematicians. And so we have to work on our, whoa, I need to work on it a lot more than perhaps you will, but let's try this again. I'm looking at my proven. Now it's kind of doesn't really say proven just yet. It sort of says prove, but what it's supposed to say is proven. And that's my way of establishing I rock, and I crushed that, and it's pretty obvious that nobody in the world can tell me that this and this does not equal each other, because I've now established that by going through the process, this shows up on both sides, and it is clearly proven that the original question was equal to this. So this first step here was a good one. So the question, of course, is, was that the only solution? And I think you probably already know the answer is no. What I've done here, I've expanded these binomials, and of course, provided I don't make any mistakes in doing that, because I haven't done anything that's mathematically incorrect, I should still be on a path that'll lead me down solving this, or at least potentially solving or proving this. So tan squared now is sine squared over cos squared, times the cos squared minus sine squared over cos squared plus cos squared. And then again, just kind of thought I'd try subtracting 1 here. I know that when I subtract 1, I know that the number 1 is the same as sine squared plus cos squared. And kind of looking slightly ahead, I could see that a cos squared, and I subtract some things here, the cos squareds would subtract out. And so similar to on the previous question now, I have a multiplied by cos squared divided by cos squared. These divide out. And so sine squared is here alone. The negative sine squared over cos squared is here. As I subtract through my parentheses, I do see a cos squared minus a cos squared. I also have a sine squared minus a sine squared. And so essentially, well, this subtracts out with this subtracts out with this, and I'm left with that same negative sine squared over cos squared, which we established on the previous question is the same as my right side. So if I worked through the right side again, assuming I hadn't already done the previous question, or the previous version of this question, right side is negative tan squared. That's the same as negative sine squared over cos squared. And again, let's go down here actually this time. So I will say that this is equal to the right side. And again, there we go, proven. That's the one I was looking for. So completely different set of steps, or at least completely different order for the steps. We saw some things that occurred here. I had the same negative sine squared over cos squared times cos squared on the previous question. But again, as long as I'm sticking with legitimate mathematical steps and I'm not making mistakes in the process, I will get there. Okay, so I won't read through, but you can see that this one I've done some similar things. This was the cos squared minus 1 is the same as negative sine squared. And then with the tan squared, I don't have a lot of option. So once again, at some point, I substitute in sine squared over cos squared. This time, I have in the first set of brackets a rational number plus 1. Typically, again, if I have two sort of fractions, I'd like to add them together and at least get to the point where I have a single fraction here. So the common denominator is cos squared. 1 is simply cos squared divided by cos squared. Once I've established a common denominator, I can add my numerators. And the numerators in this case happen to be sine squared plus cos squared, which of course is the number 1. And in the end, we end up at exactly the same spot, which we know from before. Is the same as that. And so one more time, that's equal to the left side. And so proven. Now the question of course comes up, well, what if I make a mistake somewhere along the way and go to something that's more complicated, or I didn't recognize that that I had a sine squared plus cos squared Pythagorean identity opportunity here. Well, let's say instead of recognizing that, what we chose to do is expand. So at this step right here, we chose this one right here, sorry. We chose to expand and multiply sine squared by negative sine squared, cos plus cos squared times negative sine squared. What we end up with is this line here. And while again, it's not incorrect, I think it should be clear that once I start getting fourth powers or cubes or something that I'm not used to seeing, I'm not making progress. And so the best I can say is there are certainly things you can do that will make the question more complicated and take you in a bad path, down a bad path. But you want to realize that what you're trying to do in solving these or improving these is simplify the left side, simplify the right side to the point where there's no confusion that they are exactly the same. If you're simplifying, or if you're attempting to simplify and you're getting a much more complex second step or next step, then you have to recognize at that point, well, that wasn't a good idea. Let's scratch that idea and kind of go back to, go back to this previous step and see what are my other options at this point. Expanding seems like a very bad idea. And then, of course, you have to recognize that, oh, my next option is that sine squared plus cos squared is 1. That's certainly something that should be always a key you're looking for. So you shouldn't miss it. If you do miss it, you end up with something that looks much worse than what you just had, and hopefully you recognize at that point, I better backtrack. Last one, this one was kind of dumb. I was looking for a fourth way to get started, and what I decided to do was replace all the ones with sine squared plus cos squared. Right off the bat, of course, that just contradicts what I said just a moment ago, that ideally, since I'm trying to simplify, I don't want to be going towards more complex solutions. But having said that as well, I sort of go through, in this case, subtracting 1 as we did on one of the previous examples. 1 is sine squared plus cos squared, and when we expand this and do the subtraction, it does simplify somewhat down to the negative sine squared. So we get to that negative sine squared in a different way to the one we did before. We still get there. Tan squared is sine squared over cos squared. So far I haven't done much with this. And then this is again an example of sort of where we were on the previous question. My options here are somewhat limited. I could expand, so multiply through sine squared times negative sine squared, sine squared over cos squared times negative sine squared times this, negative sine squared times this. I end up with a fourth power. That gets to be pretty messy. I could also find the common denominator here of negative cos squared and rewrite each fraction in terms of with a denominator of cos squared. But again, I think we can see that that's just getting uglier and messier. And so at that point, my only option that I can see that might be an improvement is to go a little bit of a backtrack here. And even though I substituted 1 for sine squared plus cos squared from the start, I recognized at this point that I had no choice but to really sub back the other direction. And so I'm back to sine squared plus cos squared equaling 1. Now the fraction looks like it's going to work nicely because my numerators are sine squared plus cos squared. And again, this part of the solution we've actually seen on a previous question as well. So what you're starting to see now is maybe regardless of the choice for my first step, I do a lot of the same steps in many of the solutions anyways, or many of the paths that I choose anyways. I end up with this sine squared plus cos squared anytime I used the fractions. I ended up with a with a cos squared multiplied by sine squared cos squared, and the cos squareds dividing out whenever I sort of didn't convert to sine squared over here, when I didn't make that substitution that ended up with a sine squared over here. If I just kept the original cos squared, then I had that times this and the dividing out. So there's sort of common things that will happen regardless of my first step. Oh, and I didn't quite finish, of course. I have my right side is this, which, as we've seen a few times now, is the same as what we ended up with on the left side. And one last time, proven.